Hi there and welcome again to the channel. We are doing a follow-up video to the one that we did previously on. In fact, we did two videos previously on complex numbers. In the first video, we were dealing with the definition of a complex number. Then we followed up with a video that was dealing with multiplication, addition, division of a complex number. In this video today, we want to deal with the important aspect of the modulus of a complex number. So we want to deal with number one, modulus of a complex number. And number two, we also want to deal with the argument of a complex number. We will define these terms shortly. But before we go there, remember when we were dealing with vectors, supposing we have a vector v which is equal to 3, 4. These are the components of the vector. We could take this and plot it on the xy plane. This would be your x-axis and that would be your y-axis. And we have 3 units along the x-axis. It could be there somewhere. And we go 4 units up the y-axis. So we land somewhere here. And this point here would then represent the vector. And we can, of course, join this point to the origin here, and the length of this line here gives us the modulus of the vector. And it's given, of course, by your good old distance formula. You drop a perpendicular here. Now you have got a right angle triangle here. You know this side is 4, this side is 3. So r is equal to 4 squared plus 3 squared, square root of that. That gives you the modulus of the vector. We're saying this because much the same things take place when you are dealing with complex numbers, except that you do not plot complex numbers on the xy plane, but they are plotted on a particular diagram that is called the Argand diagram, which I will describe shortly. Okay, so let's suppose we have a complex number. Again, let us call it z. And the complex number is a plus bi, where this is your your real part of the complex number, and this is the imaginary part. Now, we draw a diagram which is quite similar to the xy plane, but it's called an Argand diagram. The horizontal axis here is called the imaginary axis. Imaginary axis. The vertical axis here. Oh, sorry. So it's the other way. I really beg your pardon here. This is called the real axis. Sorry about that. Okay. And up here, this is what we call the imaginary axis. The y-axis is the imaginary axis. Okay? Right. So when you've got your complex number a plus ib, you go a units along the real axis and b units along the imaginary axis, and you are here somewhere. So this would be your point AB representing your complex number. Again, you can join this point to the origin here, and the length of this line is also now called the modulus of your complex number z. So we have modulus of z, which is written like this: z with 2 lines on either side of it is equal to, if we go back to our coordinate geometry, we know that we use the distance formula. There is our right angled triangle here. This side is B, this side is A, and therefore Z, modulus of Z, which is equal to length R, is given by A squared plus B squared, the square root of that. So modulus of Z is the square root of the sum of the square of the real part and the square of the imaginary part. A squared plus b squared. It is, of course, a positive number. It's a real number. It's a positive number. It's not a complex number because it's a distance. Okay, then let us also imagine, I'll take my, let me look for my red pen here. Okay, so supposing this line that we have drawn, joining the origin to our point AB here, is making an angle of theta with the positive x-axis. Then we know that theta, sine of theta is obviously b over r, or cos of theta is whatever. This angle theta is what is called the argument of the complex number. So we write argument, like in an argument, argument of z, and it's abbreviated to a small a rg z is equal to, if we look again at our right-angled triangle, we know that it is equal to y over x, the increase in y over increase in x, which in this case is b over a. So it is equal to arctan, the tangent of the angle whose tangent is b over a. Let me say that a little bit more slowly. This angle here, which this line representing our complex number makes with the positive x-axis, is called the argument of z, and is given by arg z is equal to arctan b over a, which of course means the tangent, the angle whose tangent is b over a. That's arg z. So those are the two quantities related to our complex number. It's got a modulus, which is equal to that, and it's got an argument, which is equal to that. Now, you will also notice that the argument, if I rotate this line here a complete 360 degrees or 2 pi radians, I'll come back here. So the argument is also, it could also be theta plus any multiple of 2 pi. So let me write it nicely. So 2k pi, any multiple of 2 pi, where k is an integer. It could be -1, it could be -16, it could be 0, it could be 13 or whatever it is. So k is an element of z, the integers. So those are the two quantities. Let's take a specific example. Okay, so what I will do is I will clear this here, but I will leave our Argand diagram as it is there. So remember, I didn't write that, sorry about that. This is an Argand, it's called an Argand diagram. It's an Argand diagram. Okay, right. Supposing our complex number z, let's say z is equal to 3 plus 4i. Now, okay, so what is modulus of z? Modulus of z is equal to the square root of 3 squared, which is 9, plus 4 squared, which is 25, square root of that, which of course is, what is it now? 9 plus 5, that's 4, then that's 3. So the modulus of z is the square root of 34. What about arg z? Arg z, let me just be careful, I might trip over my wire here. So arg z is equal to arctan this over that, which of course is 4 over 3, which of course you can evaluate on a normal calculator. Those are the two quantities related to our complex number there. Now, we can go a little further with this, and by looking at our Argand diagram there with our complex number, we notice that again here, if you have got your B here and your A here, and you are given your R there, there's another way of expressing your B and your A, because from the right angled triangle, it is clear that, let's do it slowly, we know that B over R is equal to the cosine of theta. So B is equal to R cosine, sine. Sorry. I was caught napping here. So sine of theta, I beg your pardon. Sine of theta, so we have to write it here as well. B is equal to that. So it becomes R sine of theta. What about our A? We know that A over R is equal to the cosine of theta, which means that A is equal to R cosine of theta. Now we have got A here, and we've got our B there. So we can plug them in here and write our Z now. Z is equal to, instead of A, we have R cos of theta. So we have R cos of theta. And our B, let's write our I here. Our B is equal to R sine of theta. Taking our R, which is common there, outside the bracket, we can write Z is equal to R brackets cosine of theta plus I sine of theta. So this is the polar form of a complex number, expressed in terms of its argument and its modulus there. This is the standard form of a complex number, expressed in terms of the real part and the imaginary part, the components in the real part and the imaginary part. Okay, so that's about complex numbers there. So we can come here and change from this to that, or from this to that. It's expressing the same complex number. In our next video, we will deal with another form of expressing a complex number, which is the exponential form. Of course, our aim in all this is to equip ourselves to be able to attack a typical examination question, which will come immediately after I have done the video on the exponential form of a complex number. Remember, by now, we have done addition of complex numbers, we have done division of complex numbers, we have done multiplication of complex numbers, now we have done the modulus, we have done the argument, and we are able to express a complex number from the standard form to the polar form. Let's just write it here. This is the polar form of a complex number. So polar form. Okay, and next video we will do the exponential form, and that will complete our videos on complex numbers, from which we will be able to attack some examination questions based on complex numbers. Till we see you again. Bye-bye.